Okay, so we'll start with this, and then we will go do some other ones. I'll pick some um, to try to kind of hit the major strategies we would use. In 25, there's a couple of things I think when I see this. It used to mystify me as to how you knew what to do. One thing you could do here is I could notice that I got a fraction. I have one term on the bottom. So I could rewrite this as secant squared x over sine squared x minus 1 over sine squared x. But well, just thinking about that, I'm like, I don't know. That looks, I'm not sure if that's going to work. So I'm looking to see what all I could do with it. That's one possibility I could consider. The other thing I notice is I've got squares on secant and sine. And so what I would probably do here is say, let's go look at our Pythagorean identity. So we can flip to the inside cover of our book if you don't have your laminated sheet, as I never have one, so this is what I do. If you look at the Pythagorean identities, let me write in a different color over here things I might see. Because honestly, when I first look at a problem, this is what's going through my head. I'm just kind of telling you what I'm thinking. I see I've got secant squared there. I see there's an identity with secant squared, and it's 1 plus tangent squared x is equal to secant squared x. Okay.
Or U. It says U.
Oh, U. Yeah. Okay. Yeah. So I'm just putting the x's there. Okay. Yeah, but we could use U. All right. So now I kind of go. I could get secant squared minus 1, couldn't I? If I subtracted, if I took that identity. So this is kind of like my thinking area over here. I wouldn't actually put this in my work over on the, like if I'm trying to linearly show, like a kind of little proof how I'm getting from point A to point B here. I probably wouldn't write it under that, but I might go off to the side. Hopefully you'll eventually get, or you may can already do this, where you can do this in your head. If I subtracted 1 from both sides, wouldn't I have tangent squared x is equal to secant squared x minus 1? Okay, so now I'm thinking, hey, that would be good because that takes two things on the top and turns them into one thing. So that's what I'm going to do. I'm going to say I'm going to substitute tangent squared x because those two things are equal, so I'm going to substitute an equal amount up there. That is equal to tangent squared x. And on the bottom, I have sine squared x. Okay, now that's kind of good. I know I could kind of reduce tangent to sines and cosines, and something's going to cancel out, right? Because if tangent sine squared over cosine, tangent is sine over cosine. So what I could think is this. I'm gonna put a lot of little steps in here just so you can see every little thing I'm thinking here. I'm gonna write this here. And just because I know that I'm going to end up with a complex fraction, and I don't like complex fractions, they tend to confuse me, but, we could handle them. But this is one way you could get around it. I could say that's tangent squared times 1 over sine squared x, right? Okay, all I'm doing is just breaking the numerator and the denominator apart. I could just say the numerator times 1 over the denominator. That's an equal amount. The reason I did this is to avoid a complex fraction. You wouldn't have to do this. You could go, thanks. You wouldn't have to do this. You could have just put a big old mess up there on top in the numerator, but if you don't like it, we know tangent is sine over cosine, so tangent squared would be sine squared over cosine squared. And now I'm just going to write this other thing that I had over there, times 1 over sine squared x. That's a times there. Now I don't have to mess with the complex fraction because I just split it up like that. So that's one way to avoid them if you hate them. Most people do. Okay. So now what cancels out? See, they go away. It's really algebra. It's substitution of equal things in place of something else. And then it's just simplifying after that. So I get 1 over cosine squared x. And what's the reciprocal function of cosine? So wouldn't this be, if I have 1 over cosine, isn't that what secant is? So it would be secant x, but it's going to be squared because it was cosine squared. So that one actually matches up with, which one in your book? Let's see, it should be secant. Oh, E. Yeah, this is on that second little set there. So E is secant squared. Remember, if I kind of look at that for a minute, there's a way that I can take care of this. Now, it may be on your identity list. The reason it's so coming to my mind, it is on your identity list. In the back of the book, too, it's there listed under co-function identities. The only reason that this one really popped out to me really quickly is this is what the geometry students in their book had a proof over this. And so we've done it. I've done it recently with them. And it was kind of interesting what they had them do to see this. Do you remember that the sine of an angle is equal to the cosine of its complementary angle? And if you think about it, sine of 1/2 is equal to sine of 30 degrees is equal to the cosine of 60 degrees. And if you looked at your tables, you see that those numbers are in both columns, right? They're just flipped, kind of. So when you see like 90 degrees minus an angle, they've got an identity back there for you, but I can tell you right now that's going to be the cosine of whatever x is. So that would simplify really quickly. That looks kind of gross, but if you look back under cofunction identities on your back page, it's right there also, if that is not kind of making sense. So what I have now is cosine x, and then I have cosecant x. Why did I write in red? I do not know. All right, so what should I do now? If all else fails, remember one of the big ideas is rewrite in terms of sine and cosine. Because that's kind of one way to get everything in, reduced down to stuff that maybe something will cancel out in. Well, I got cosine. What's cosecant x? It is, so let's write it that way, 1 over sine x, right? We'll just substitute that in. So that's cosine x over sine x if I put them together, right? Y'all know what that is?
That's cotangent.
Cotangent, yeah. Tangent is sine over cosine, so it's flipped. If I flip tangent, I get cotangent. So that's just the cotangent of x there. Okay. I look at this, and here's what I notice. Remember, we're not treating this like an algebraic equation, are we? We're taking the first part, and we're trying to make it look like the second part. So it's like, on my last step, I should have this, and I'm starting with this. So I'm going to rewrite it just to emphasize that, because I know in the past I thought students understood that, and maybe they didn't. All right. Notice that I got 2 terms, and it goes down to 1 term. Sometimes when that happens, you can factor something out. Do y'all see anything you can factor out right off the bat, though?
Not really.
Okay.
The only thing I could think would be to change the cotangent to cosine over.
Right. Everything else is in terms of sine and cosine. Yeah, that's what you want to try next. Because you try what you can think of, and honestly, that's all I can think of here too so far. Because maybe something will factor out if I do that, or something will cancel out, and abracadabra, things look nice and pretty again. So cotangent would be what, cosine over sine?
Yeah.
Okay. Okay. So here's what we have now. Okay. I see a square in there, and that makes me think maybe there's going to be some kind of identity I could use, except the problem is I don't have sine squared, right?
But can we put it over a fraction and then multiply both sides by sine?
Well,
To get a common denominator?
yeah, that's exactly. I thought you were saying something else, but yeah, that last part, that's exactly what we want to do. We got one of them being a fraction. Let's turn the other one into a fraction, and let's put them together and get a common denominator, because we know these 2 terms somehow have to go down to 1 term, so getting a common denominator would make that happen, wouldn't it? So we'll multiply by sine theta over sine theta just on the first term. Good. And when we do that, we do get sine squared theta plus cosine squared theta on top, and on the bottom I've got sine theta, because it's my common denominator. Now I have 2 square terms on the top. What's sine squared theta plus cosine squared theta equal to? And how'd you know that? Yeah, it's a Pythagorean identity. When you see squares, go straight to those Pythagorean identities most of the time. 99% of the time, that's what you're going to do.
Look at there.
Yeah, look at that.
Now we have this.
Now, 1 over sine theta is. Uh-huh. So maybe we thought we might want to factor something here. That didn't work out. We changed it to sines over cosines. Look at it, still nothing happening. So we say, oh, there's a fraction, get a common denominator, right? And when you do that, abracadabra, everything falls into place. So it's just seeing that some of your major strategies are there, okay?